Hello and welcome. My name is Gerhard Zwolber. I'm a data scientist and book author at SAS. And in my webinar today, I'm going to show you how you can apply analytics and data science for your business questions. Over the last years, I have written 3 books for SAS. My first book covered the data preparation considerations for analytics and data science. Next, I wrote the Green Book, which dealt with the data quality considerations for analytics and data science. And finally, in my Applying Data Science book, which we're going to talk about today in this webinar, I collected data science case studies, how you can apply methods for your business and make better business decisions. So today we're going to focus on examples, how you can use this, and my plan is to give you an overview in this webinar. I have recorded more sessions on that. So the data science applications and case studies range from applying survival analysis or using regression analysis for forecast errors, running Monte Carlo simulations to get a better picture on the outcome distributions, listen to your data and let your data talk with unsupervised machine learning techniques, using text analytics, and many more topics. These are all relevant applications, and in this webinar I would like to give you an overview about them. If you're interested in more details, you can always navigate to my webinar playlist at YouTube, where you see individual, more detailed presentations on all these particular topics, and you will find a link for this playlist in the download section to this YouTube video here. Let's now start and let's take a look on data science in action number 1. The idea that I'm showing here is to use survival analysis to perform headcount analysis for employee retention. So this case study answers the question how you can draw conclusions and make assumptions about the average length of a time interval, even if some endpoints are not yet fully observed. In this method, I'm using kaplan-meier methods and the proportional hazard regression to get a clearer picture on how long employees are staying with their company. The idea of this case study is also to use a method which is already very well established, for example, in medical statistics, survival analysis, for other business applications, and which also shows that statistical methods can be applied in many different areas and can answer also business questions in different fields. Let's take a look on the content of this case study. What you see here in this chart are the careers for various employees. So each horizontal line represents the career of a certain employee. So we see here, for example, the career of an employee who started here and who is at the end of our observation period still with the company. We see here another career of an employee who started here and who left the company at this date. So you see we have long and shorter careers for different employees. Some of them already left the company, others are still with the company. The point now is, if we go and draw conclusions now about the average length of our retention time of the employees, we quickly find out that we have to define something for those employees who are still with the company. Are they going to stay 1 more month, another year, another 2 years? But we will also very quickly find out that any assumptions we make heavily influences the outcome of our analysis. The method of choice here is the kaplan-meier method. The kaplan-meier method allows to deal with censored data. It allows to consider both those careers which already have an effective end date and those careers who are not yet ended, who need to be censored. And Kaplan-Meier methods allow to draw retention curves for employees and compare, for example, different groups where you see that, for example, sales representatives have a much lower retention time compared to sales engineers. So the Kaplan-Meier method allows you here to give an indication about what is the average, what is the median, but also compare it between groups, departments, or income levels. This method also allows you to detect different episodes over time in the career of your employees. For example, what you see here in the hazard curve, which represents the risk of an employee leaving the company, we see, for example, for the blue curve, the sales engineers, that we have different peaks here. So, for example, we have a peak somewhere here after a little bit more than 2 years, and another peak a little bit after more than 4 years. This can be interpreted from a business point of view, saying that maybe after 2 years, some employees are leaving because they're disappointed for not being promoted after 2 years, not getting the expected raise after 2 years, and we see a little bit larger peak for the employees here after 2 years from the sales engineers department leaving the company. The same might be, a similar thing might be true after 4 years, where maybe some employees find out they have worked in this domain now for a while, they would like to move forward, change to another company, maybe have an additional line in their CV and being able to show more experience in different companies. So you can use this method also to find out when are you at high risk to leave the company. Survival analysis not only allows you to compare different groups and to detect certain points over time, it also allows you to generate predictions. So, for example, when you have certain risk factors, in my analysis I have department, gender, and the fact whether someone has technical know-how, to find now out for certain employees, for example for Gerhard, what is the expected survival time and what is the probability to resign within a certain period. So running this analysis, we receive probabilities, which we now can use to compare different segments of employees or to order them by risk, and to see which employees are at high risk that they cancel. So what we see here is a very interesting application of a data science method, survival analysis here, and being applied not on medical data but on employee data. Let's now move forward to the data science case study number 2. Here I'm featuring how you can use data science method to detect structural changes, for example breakpoints or outliers in longitudinal data. So the idea here is to find out, can we detect events and changes over time automatically in the data by analytical methods and not having to review the graphs all manually and visually. Here we are going to use ARIMA models with outlier detection and also multivariate adaptive regression splines for the breakpoints. Let's take a look how this looks like. The idea here is, as I said, for example, to use ARIMA models to automatically detect outliers in the data. We see here a time series which has a certain upward trend and a seasonal pattern, and at some point in time we see that the passenger numbers drop substantially. You see here that this is the point when the 9/11 event took place, which is automatically detected here in the data. However, it also detects changes over time, which happens later when the passenger numbers increase again and when they return to certain levels over time. A similar thing can also be done when you consider the time series over time to detect where do certain breakpoints happen, where maybe the time series changes its average course going down, going up. This can be done by multivariate adaptive regression splines where you can analyze your data in more detail. I would like to show this example with more explanation. The data that you're seeing here is data from a clinical trial. So the red line represents the recruitment numbers over time, and we see at the beginning we have quite a steady line, then the red line goes down, goes up again, and then continues over time. If we run automatic breakpoint detection on the data, we see that automatically some breakpoints are detected here. And for example, the first one, which is automatically indicated here by a horizontal line, if you relate that to the business content, is that here at this point in time, one patient had a very severe adverse event in the clinical trial, and a big discussion came up whether this severe event is possibly related to the study medication. Consequently, over time, the recruitment numbers went down because there was quite some uncertainty, and the clinical centers were not so willing to recruit new patients into the trial. Then the method detects another point, and this is exactly the point in time where a study meeting took place and announced, after analyzing all the data from a safety perspective, that this event is not related to the treatment. And you see after this, the event takes place, that the recruitment recovers and then continues with something like almost normal. What we see here is a very interesting example that shows that you can use analytics to automatically scan your longitudinal data and to detect events and maybe structural changes and breakpoints over time where certain things took place. In the third example, we are talking about the topic how you can use analytics to explain the errors from another analytical model. In this case, I'm showing here how you can use analytics to explain forecast error from a time series forecasting model, and also dealing with the question whether the demand planners, when they apply their manual overrides, whether they improve the forecast accuracy or when they decrease it. Let's take a look how this can be applied. We have here a time series, which you see here in yellow, where the forecast is made for certain months, from April, May, June, and July. We see then the actual values, for example, here in April as a blue dot, which lies a little bit higher than the forecast, also in May, a little bit lower in June. And the idea is now whether this difference from the actual value down to the forecasted value, whether there's a relationship which you can learn, which improves your knowledge and your trust in the forecast, which maybe depends on the product group, on the product age, on the target calendar month, whether the forecast was made for a particular calendar month or for another one. So to study the deviations from the actual to the forecast value based on certain influence variables. This is the idea which has been applied here. This allows you to gain a picture to see, for example, here over time, the larger or the longer the data history of your products is, so the more information you have, so with increasing product age, the forecast error goes down. So this is something which can be learned from this analysis. You also find out that there are some product groups which usually have a quite small forecast error compared to certain product groups which have on average a larger forecast error. And you see the same, for example, for launch months, that there are certain launch months, for example, in July, which have on average lower forecast errors compared to other months in June, where you have on average larger forecast errors. Data science methods can help you to study these relationships, but also then to formulate them in a linear regression model and then allow you to make predictions if you have a certain product forecast for a certain month applied on certain historic data. What is the expected average value in forecast error that you are going to achieve here. There's another application how you can that deals with time series forecasting, and this is data science in action number 10, where you see how the forecasting for how forecasting the demand for new products can be applied. So the idea is here, how can you estimate the expected demand of your product for products that are only right now being introduced in the market? Can there still be made some estimations? The idea here is to apply, for example, Poisson regression based on other variables, or to perform similarity search to detect similar products where you can transfer the forecast from the similar products to the actual product. I'm presenting here a slide which our customer Swarovski has presented at the AX conference 2012 in Cologne, where they exactly perform where they exactly use this method. They call it novelty forecasting, where they analyze the expected value of the forecast, the expected value of the demand for the next month, based on product attributes, time-dependent attributes, the number of shops in which the product is going to be launched, and other variables. This allows also to achieve demand forecast for products which do not have a substantial time history, but only have a very small history, where you still can use other features to derive an estimation of the forecast. In our next example, the idea is to listen to your data. Here we are going to apply unsupervised analysis methods, for example, association analysis or variable cluster analysis, to listen to our data, to allow our data to tell us stories without having to ask explicitly every question and every detail. Let's have a look on how this can be achieved. The data that I have here is data from car insurance, where I have 6 properties for my customers. For example, the age, the gender, the area where the person lives, highly urban or rural, the car type, the car usage, and the fact whether someone had a claim or not. Usually when we take a look at this data, we are very often tempted to say, okay, this is a typical data set for supervised machine learning. We would like to perform predictive analysis whether these attributes here have a relationship to the outcome. Definitely, this is something which you often would like to do and analyze, for example, in actuarial statistics and other methods. However, in many cases, it also makes sense not to select one particular variable as the target variable, but to study all variables together to see whether there is a certain relationship in the data which might be interesting for you. So you can use, for example, association analysis to treat the data like they were generated in market basket analysis, like all the attributes one customer has. He is young, he is male, he drives a sports car, does he have a claim, yes or no? So to get the relationships of the attributes out, similar to market basket analysis. Let's have a look at possible results that might come out of such an analysis. So association analysis gives us the results here in rules, which says the fact that a certain attribute is available in the data. For example, a van is driven. The fact that this is driven by a female person. How often does this appear in the data? What is the expected confidence of that? And is it higher or lower than the expected confidence if we would treat these attributes as 2 independent occurrences? Let's have a look here at the sorted list at the very end. So we see here all the rules that came out of my data, and we look at the very end of my list, and we see here a lift which is very low based on the rule sports cars are driven by mail occurs extremely seldom. We would have expected that this occurs in 46% of the cases on average. However, we only see truly in the data in 2.5% of the cases. So we quite a difference from the expected to the actual representation in the data. And we might now find out why there is such a difference in this rule, and may generate some hypotheses from a business perspective what the reason might be. For example, it might be that in our customer base, it's really the case that sports cars are mainly driven by women. Might be the case. It might also be a trigger to say, if we see this, we cannot believe, maybe it makes sense to investigate in more detail the quality status of our data. Maybe we find here something wrong. It might also be the business reason that maybe in a family, the sports car is the second or the third car in the family, and this is for financial reasons registered on the wife's name or insured under the wife's name, and thus we see this here in our data. Or we see here that the consequence that competitors might be offering a policy to men at a much more attractive price. So men who would like to insure sports cars do not come to our insurance company, but go to another insurance company. And this might be something we are seeing here, and where we have the data talking to us and see this as a consequence. So what we have seen here, we did not formulate any prior hypothesis. We just performed explanatory analysis and let the data talk to us and see what possible outcome might be that might be relevant to us. Let's now take another look on the possible alignment with predefined patterns. So we're taking a look on data science case study number 5, and we would like to see which customers or which analysis subjects have a behavior which is far from what we expected. This is an area which often is found, for example, in financial and tax analysis as the Benford's law, and the method that we apply here is very often just simple chi-square independency tests to see how far is the actual representation, the actual distribution from the expected distribution. Let's have a look how this can be applied. Consider a company which has sales representatives, and let's assume this company is active in the catering business or in the leisure business, and the sales representative have the job to subcontract companies for over the calendar year. So to make sure that the company has enough buffer, has enough capacities in a certain times over the year. We can see here that the historic demand over the calendar months looks like this. So we see we have here quite a peak in summer, we have a peak here at Christmas time, and we have some here at the end of the winter season. So for example, this might be maybe some leisure activities in the Alps, where you see, okay, we have a Christmas peak. We have a peak when the winter holidays in schools take place, and we have in summer. This is also a predefinition how our sales representatives should contract other companies and make sure that we have enough capacity in our country. Let's take a look on this chart as a line chart, which now looks like this. And let's now see, when we look what is the expected value, which we see here in black, comparing this with the actual individual lines per salesperson. If we look at the individual lines, this is not really helpful because this is quite crowded and it's hard to find, to pick any patterns out of this. However, when we apply analytics and we say we would like to rank all the salespeople who is most close to our predefined expected pattern, who is farthest away from that, we can very easily go and say this gives us a much better insight. So for example, when we rank them by the top 10 salesperson adhering to the pattern, we see these are the 10 account managers who are closest to our black line. You also can see who are the 10 salespersons without any seasonal variation, who do not consider any variation, but have their contracts very evenly distributed over the year. We can also look at the other end of the analysis list and see what are the top 10 salespersons who are farthest away from adhering to the pattern, who almost work against the predefined pattern. So what you see here, chi-square test, very simple analysis method, but it allows you to run an analysis and rank your analysis subject, in this case your salespersons, based on how close they are with the predefined. So in a nutshell, you see here that analytics helps you to get a clearer picture, because we start with noise, we perform analytics, and end with manageable segments. And this picture is a very good one to see how analytics and data science can help you to get a clearer picture and to understand things in a better way. Let's now take a look on data science in action number 6. This is an idea where you can use analytics to calculate a reference value which considers the details of subgroups and all available co-information. The idea is that these methods allow you to eliminate the yes but sentences that you often hear in your business discussions, where you say this is the expected value for that, and then business says yes but in this case we very often have in this month we usually have higher or lower values, or this group of analysis subjects have a harder time to fulfill the policies because they have certain features. The idea is to use analytical methods to already include all these covariables in the calculation of the expected value, and to eliminate these discussions on the yes. So what you, for example, have here is that if you look on a time series, you see that we have a certain trend, and we also have a certain seasonal pattern going on here. And if we now flag certain observations for outliers, for example, this value here in February is indicated as an outlier. However, this value here in January is not indicated as an outlier. This is due to the fact that the model, which indicates whether something is an outlier or not, already considers the trend, the seasonal pattern, and maybe other systematic changes in the data, and only flags those which are really far away from their individual expected value, and not say I use one average which has to fit all observations. This can also be applied not only on time series data, but also on other observations, where I have here for a certain number of patients the cholesterol value, where I just aligned the patients randomly on the horizontal axis. And we see here what happens if I just use an overall limit. So this would be one limit which fits all, compared to an individual limit. And this individual limit is calculated based on the gender, on the age, on the stage of the tumor, and on the participating center. So it allows us to calculate individual groups and individual expected values. So we see here that some of these values are outliers and should be considered as outliers because they are really quite far away from the other values. However, we also see groups where these values would not be considered as outliers if we use the overall limit, but they are lying inside the individual limit. So they might be detected or classified as outliers with the overall limit, but not if we have individual confidence limits. So this is a way to have this more precise and in a better way to have it. Same here as maybe overlooked outliers. These values here in this group are not classified as outliers because they lie within the overall limit. However, they are above their individually expected limit and might still be outliers even if their values is not that high, but compared to their peer group they are very high and should still be flagged. Let's now come to another case study number 7, where we see how we can use text analytics and topics and search for topics in documents and cluster them. So the idea is, can you automatically find clusters of documents with similar content without having to read the documents manually? This is the world where we use text analytics, for example, text mining, natural language processing, and text parsing, where we analyze the content and the frequency of words and also perform semantic analysis based on that. I have applied this on my first 2 books, on the data preparation book and on the data quality book, where I text mined all the individual chapters that I found in the books. And I asked the SAS text analytics solution to automatically cluster those documents or those chapters together, which are very similar based on the analyzed content. So you see here those chapters that have been grouped together into one segment by the text analytics solution, and we see from the short content description here that the topics are here accessing the data, the origin of the data availability, which you see which comes from a different book, but from the content perspective this is very similar to the other chapters. So what happened here is data science method text analytics allows to automatically study the content of documents and group them together into meaningful groups. And I reviewed all the groups that were created here, and I was positively surprised how meaningful they are and how really very well my book content was clustered automatically by text analytics. In data science case study number 8, we're going to see how you can use Monte Carlo simulations to get a clearer understanding of the outcome distribution. In this example, I'm presenting a case study where the sales manager looks at his project pipeline, where he has listed a couple of projects, and he would like to see what is the possible outcome. Maybe some projects are coming, others are not coming, and having a clearer picture than just looking at the average or the expected value, but to perform Monte Carlo simulations to see this in more detail. So what you see here is that we have 21 projects from our sales manager, and we see here the expected deal size in $1,000, 1.5 million, 10,000, 500,000, and also the individual probability the sales manager estimated that this project might be closed. If he now has to see to come up with a decision, what is the average number of dollars, or the average amount of dollars I'm going to make by the end of the year, he might now go and say, I'm going to weight the deal size with the probability, sum it up. This gives me some impression. Yes, this gives him some impression. However, this might be quite biased, this 1.6 million, by just averaging and summing this up, because it might be the case that maybe this project is coming, this project is coming, this is not coming at all, this is not coming at all. So at the end, projects will not contribute with their weighted number, but with their full or with their zero number. And if you consider this, that they only contribute with the full or with the zero number based on your probability, and you run a Monte Carlo simulation, you quickly see that the distribution looks much different. For example, lots of them of the scenarios with their values are in the lower value segment, and only few of them are in the higher value segment. So we see that the weighted average of 1.6 is quite misleading. So you might see, okay, on average I might achieve something like that. However, there is quite a substantial number of cases which are left from it and which will not generate enough business for the sales manager, which allows him to survive the next year in his company. Let's now come to data science in action number 10, and this is an idea how you can study complex systems, for example, the Monopoly board game. The idea is to show that you can use Monte Carlo simulations to study environments or setups which are hard to study just by reading the rules or just by imagining all the rules. And this is a very good example how you can use analytics in Monte Carlo simulations to say, I would like to get insight in the most frequent processes and the most important relationships in my system. I have done this based on the Monopoly board game, which is a very good example to demonstrate, because Monopoly consists of a set of rules. There's a framework of opportunities and events which happens while you're playing and while you're circling around. There are also additional instructions that you have to follow, like in real business life or like in real other scenarios. There's also a random component as you're rolling the dice. There's also, in this special edition of Monopoly, a dynamic component which also changes its behavior during the game. And of course, very important also for simulation case studies, there's also a monetary dimension as you use money to as you use money for playing. If you now apply a simulation case study, a Monte Carlo simulation on the Monopoly board game, you can many different features here. So for example, what is the visit frequency on different fields of the Monopoly board game? Or what is the profitability of different fields? Maybe some fields are cheaper, but they are not visited that frequently, and also the expected income is not very high for that field. What you see here is a simulation scenario that I ran by rolling 2 dice, by following all the directives like go to jail, and also considering the event fields, and also by considering this special accelerator dice for my special edition of Monopoly. And what you see that after playing a large number of rounds, so this is the simulation results after playing 70 rounds, you see that the visit distribution on the fields of the Monopoly board game is far away from being evenly distributed, but there's quite a difference that some fields are very often visited, for example this one, and a couple of others, whereas others are not very often visited. So this is insight which would be hard to get just by reading the instructions or just by studying the Monopoly board game setup, and this is a very good example how Monte Carlo simulations give you insight in complex processes that would otherwise be hard to detect and hard to understand. We are here coming to the end of my presentation, and what I've shown you in these 10 short examples on how you can apply analytics and data science on your data is that analytics helps you to get a more objective picture on your data and analysis subjects when you analyze it. So it is more objective and more precise what you get here, who is on the top of the list, who is below on the list, and you get data-driven results. The important thing is also here that you get explicit results automatically delivered. So you do not need to have to ask all questions manually, but you can make your data talk to you and get the explicit results delivered instead of having to filter and to search and to subquery all different segments and all different setups. But analytical methods, for example, like the outlier detection, can automatically talk to you and say, I found these 5 points and they should be checked, and you do not have to do this all manually by filtering. As I said, the important thing is here that you can do this automatically instead of manually, and all these models in the SAS Analytic platform are set up to be able to rerun and to be monitored frequently over time, because in many cases you're not only interested to run an ad hoc analysis, but you would like to rerun and to remonitor your analysis over time if you run it more often. So what I've shown you here is just the overview of these 10 case studies. You find a more detailed presentation on each individual case study in my data science webinar series, which can be accessed at YouTube in the playlist. You find the link on the playlist at the in the link section of this video. I'm also frequently publishing articles at SAS communities on these topics, where, for example, here, as I demonstrated earlier, the method to detect the breakpoints over time automatically. There's an article that I wrote with SAS code how you can do this, and there are many other articles that I wrote which can be used to reproduce the results and to get more insight into that. I'm happy if I could gain your attention on all these topics. If you would like to see more, as I said, take a look at our DACH YouTube channel. You can also follow me on LinkedIn and on Twitter, where I always blog and post on data science analytic topics. I'm also publishing content, for example, all my programs, all my data sets for my books on GitHub, and more content can of course also be found in my SAS Press books. Thanks for watching, and I look forward to welcome you soon to another data science webinar.